Science and Technology Association, that is YASTA, was founded in 1988 with an aim to promote, encourage, and develop the growth of aerosol science and technology disciplines and their application in our country. So, an important part of YASTA mandate is to provide a platform for reporting and discussing new developments in aerosol science and technology and associated areas. So for this, we are conducting programs and activities, including YASA conference in different parts of country. One of the steps in the conduction of online lectures by well-known aerosol scientists and engineers on monthly basis. I heartily thank all YASA members who are devoting time to make this series a grand success. In continuation of YASA monthly online lecture series, today we'll be having the 14th lecture by Dr. Sarath Guttikunda. The title of this lecture is Aerosol in India, Inside Data Resources Modeling and Research Opportunities. To brief about Dr. Sarath Guttikunda, he is the founder director of Urban Emissions and is an adjunct professor at the Indian Institute of Technology, Delhi, India. He is the recipient of International Award by the American Geophysical Union AGU in 2022. It is given annually in recognition of the furthering the earth and space sciences for the benefit of society in developing nations. He conducts research in an independent capacity at Urban Emissions to support science and public policy dialogues on air pollution in India and cities across Asia, Africa, and Latin America. He received his bachelor's in chemical engineering at the Indian Institute of Technology, Kharagpur, India, 1997, and PhD from the University of Iowa City, USA, 2002. So this is over to Dr. Sarath Guttikunda for the lecture, and everyone is waiting to hear from him.
Hi. Thank you, Sunita. Thank you, Neeraj and Manish, for inviting me for this lecture. Thank you. What I will do is I'll basically go through some of the work that we've been doing, and then I'll open up to some research opportunity questions that will be very useful, especially for the students who are on this platform, and how to take this forward. This is an article that I wrote in 2019, one of the generic articles that I've written in a very, very long time. It's about what are the three kinds of people that we need to manage air pollution. And it's not about just in India, but wherever. One group is the feeder, are basically the collectors of information, people who do a lot of data collection work and do the interpretation work, mappers, scientists, doctors. Everybody is collecting information. Anybody who's collecting information, anybody who's feeding the science, the science part, they're all basically our feeders. Basically everybody on this group in this lecture right now, so they're all basically our feeders. So I have the next group are basically drummers, or otherwise noisemakers. When scientists nowadays are also writing their own articles, especially in the journals, and they also make a lot of noise on what kind of science are they doing, what are they finding. And generally speaking, this part has been given to journalists only, but that space is actually expanding quite a bit. And then you have the changers, the decision makers. So this is pretty much uh, dedicated to the government offices. They are the ones who are making the decision, but they make the decision based on the information they're getting from the feeders and the information they're getting from the noisemakers. So typically speaking, we have a lot of noisemakers. We have a very small group of feeders or collectors. As you can see, we have barely 80 participants at this moment. That's very handful of people. But if you start looking at this is a very niche group that we are really speaking to. But the decision makers are even more smaller, because there's the decision makers who are sitting around the table, they're taking the decisions. But this is where I think my punchline of this presentation is all about the feeders. Like we need more feeders. We need more people doing hardcore science, hardcore analysis, hardcore interpretation of the information that we're getting from various venues. At Urban Emissions, we formed in 2006, and we basically do a lot of number crunching. As it says here, we are full-time feeders and then part-time drummers. When we are not journalists, I mean, we are basically we do some PR around the work that we are doing, but 100% most of the time, what we do is basically number crunching, generation of information, and literally around air pollution. So we don't do any of the other fields like water, soil, and other things. One of the umbrella programs, assuming that a lot of people are familiar with this, the Apna City program, air pollution knowledge assessments. Under this, for cities especially, we collect a lot of information on their landscape, geography, meteorology, and we build a baseline emissions inventory and a baseline meteorological data collation, and use that through a chemical transport model to do either both spatial and temporal analysis, and then use that information to do PR, knowledge sharing. Now, if a group says, okay, we are interested only in source apportionment, then we provide the pie of saying, okay, this is the source apportionment that we calculated based on the meteorology and the local information in the emissions inventory. Some groups will be interested only in the inventory, then we can focus only on the inventory. So depending on the group that we are talking to, or whoever approaches us, the kind of knowledge sharing keeps changing. But the baseline is around this. The PR part, the noise making part is basically this. So we provide some very simplified leaflets for each of the cities, where if you open the leaflet and you look at it, you know what should be the size of the airshed, what kind of information is already available on the emissions, what are the highlights in terms of source apportionment, and how much work is happening on the monitoring data. So very simple information is provided all in the leaflets. So all of this is online. It's easily accessible on our website. And we're now expanding this to the NCAP cities, the National Clean Air Program for all 131 cities. The methodologies are all the same wherever you go, whether you're working in India or Asia, Africa, Latin America. So we have expanded this program to a lot of other regions as well. So all it changes is your input. How do we massage the data that we're getting from different sectors? How do we make it talk to each other? How do we, if there are any gaps, how do we try to fill that gap in building the inventory and take it forward? So every region has their own problems. Like in India, we have our own problems, but we try to bridge that gap. There is always the concept of combined co-benefits between air quality and climate change. It is a area where you can go back and forth. But in this talk and primarily in our work, we pretty much stick to air quality, where the changes that we are seeing on the ground in the sectors are more immediate. So if we cut down emissions at the source, we obviously will immediately see the changes in the air quality in the neighborhood, or over a long term in the regulatory framework as well. So in India, we have defined a lot of criteria pollutants. This is just a summary of that. Most of the time, we are focusing on the particulate matter, PM2.5, PM10, and we also have a lot of science work that's happening within the fractions of PM2.5, PM10, that is BC and OC, black carbon, organic carbon. And we also have inorganic portions in this PM2.5, which is nitrates, sulfates, and ammonium, which is coming from the gaseous part of the air pollution. And all of them have standards for 24 hours, or hourly, and for annual basis. And that's the regulatory side of the work. But from the science side, what we're interested in is actually in the break of this portion. Majority of our discussion is focused on PM, especially on PM 2.5 and I'll come back to this slide after some time. and how PM 2.5, PM10 plays even more stronger role both in terms of science and the regulatory purposes. Mm. But when this is a known fact that PM is an important pollutant in India, and most of the regulatory work is circling around PM 2.5. And if there is a policy to control PM, which means that it invariably includes the contributions from other gases as well. So, VOCs are contributing to SOA, secondary organic aerosols, SO2 to sulfates, NOx, nitrates, and ammonia to ammonium. All of them are part of PM 2.5. So if we want to control PM 2.5, so we really have to we will have to go after the gases as well. So that's one of the reasons why PM becomes a very a central figure in all our air pollution discussions. And also from the health perspective, it's the largest contributor to all our health impacts. This is the latest report from the Health Effects Institute, State of Global Air, and the numbers are again very high, second only to China compared to in terms of overall like estimated mortality and other morbidity effects. And this is a study that was done by Terry a few years back, looking at how much the respiratory, the immediate impacts of PM 2.5 are increasing, especially in Delhi. So if they basically tracked hospital admissions that are happening at various hospitals, and then the trends in the ambient average PM 2.5 pollution. So if any given day we are going from 60 micrograms per meter cube to 225 micrograms per meter cube, which is not unimaginable. It happens quite a bit in most of the places around Delhi and a few other cities. So we have a 11% increase in the clinical visits. I mean, that's a huge number. I mean, if you're talking about 10 people visiting every day, when these pollution levels go up, especially in the winter time to 200 plus micrograms per meter cube, we have a 10% increase in the number of people going to the hospitals. And this is a study from University of Chicago on the air quality life index, how much life expectancies are we losing because of these high trends in PM 2.5. That's about 5.2 years estimated. And like this, we have a lot of impacts that are there. And all these studies are happening. But again, this is more, again, on the top end of the story. We have the pollution and we have the impacts. Now, where is this pollution coming from? So this is where we have to be a lot more stricter in our science messages, saying that, okay, anything that burns is emissions and it results in pollution. Okay, so it's not about whether that burning is happening in the transport sector or industrial sector or household or the waste burning at the landfills. If anything is burning, it basically produces emissions, and that is going to end up in the pollution. So if we really want to, like mathematically speaking, this is the pollution is equal to mass over volume. Volume of air we can't control. Okay, what we can control is the mass of emissions, how much emissions are coming from burning of any of these fuels, irrespective of where they're being burnt. Okay, best example is during the COVID times, those lockdowns for those 2 months. These are satellite observations from Tropome and MODIS. And when you can see immediately, both from the aerosol optical depth, which is the aerosol loading in the entire column, and also from the nitrogen dioxide NO2 loading in the entire column, the drops are phenomenal. Okay, in those 2 months, we saw it drops from 30 to 50%. This is only over Delhi, and similar studies are there available for all the other cities as well, and on a regional basis. So all this says is basically, if we cut down emissions, irrespective of the sector, we will have benefits in the pollution. Okay, so it's not about controlling the pollution; it's about controlling the emissions. Now, in India, let's do a quick recap of where is this PM 2.5 pollution and where do we stand. This is results of a reanalysis field from the University of Washington St. Louis group, Randall Martin's group, looking at the trends all the way from 1998 to 2022. And this basically includes a combination of emissions inventory work, chemical transport modeling using global geochem model, and a lot of nudging from all the available satellite feeds. So it includes a lot of information from the ground monitoring data, satellite monitoring data, and understanding of all the bottom-up inventories. So it's very clear that going from 1998 to 2022, things have really went from partly green and yellow to very high red and brown all across. In the Indo-Gangetic plain, obviously the numbers are a lot more darker than in the other places. And all the extracts from this study for the India by the grids and by state, they're all available on our website, so you can immediately download and use it. So a quick look at now how this has changed both from the total pollution exposure in the region and to the total population exposed to these pollution levels. Generally speaking, the compliance to the national standard from basically reduced from 60% to 28.4%. Okay, so that's we literally uh, doubled our pollution overall in these 20 years. And then population exposed to poor to severe pollution levels, as in when these are the categories we have in our air quality index, to that pollution basically increased from 0% in 1998 to close to 20% in the in 2020. So as you can see here, the bottom line, these red ones basically, this is the poor pollution, poor and severe pollution. It really has dramatically increased. And the total population basically went up, and exposed to that pollution is 20%. And this is primarily coming in the Indo-Gangetic plain. And the percentage changes are basically coming from everywhere, not just from sorry. So it's not just coming from one sector, it's coming from like all the sectors. So if we just quickly look at, again, this is where the numbers game comes in, right? So we may be introducing a lot of new technology and a lot of emission control measures and a lot of resources to control the emissions. But at the same time, we are increasing the number of the number count in the total burning of these different fuels. So it basically increases the overall the load of these emissions, and then of course the pollution also goes up. So here's a quick look at the transport sector between 2000 and 2020. Overall, the two-wheelers and four-wheelers increased 6 times. So even if we are increasing, bettering our vehicle standard, we were almost at no Bharat standards in 1990s to now we have Bharat 6 in 2020. We increased that quite a bit, but we also increased the number of vehicles on the road, which means that whatever benefits we're getting from the technology, we are basically losing all that in the number of vehicles that are going onto the ground. Same thing on the vehicle usage as well. So I mean, I'm putting these two figures next to each other because when we talk about transport sector and emissions inventory, it's a combination of both the number of vehicles and vehicle usage multiplied by emission factor. I mean, we are bettering the emission factor, but we are tremendously increasing the number of vehicles and the vehicle kilometers traveled, which means that whatever benefits we get in a clean emission factor, we are basically nulling it out really fast, and emissions are continuing to grow in the transport sector. And looking at directly from the fuels burnt, the only fuel that actually reduced its consumption over the years is the kerosene. I mean, we actively promoted for not using kerosene in across the country, especially in the rural areas. And I think that credit pretty much goes to having better lighting infrastructure, the transmission lines going to rural areas, and increasing the electrifications percentages that basically reduce the use of kerosene for lighting, and of course, automatically a lot of the cooking and heating sector also benefited a lot from that. But apart from that, if you look at all the other fuels, now petrol has increased, diesel is continuing to increase. Now ATF, that's the aviation fuel, that's also increasing quite a bit. The LPG is also increasing, which is an excellent sign. basically that's the cleanest fuel we have among all of these. But whatever benefits we are expecting from use of LPG and kerosene, other fuels are going up so much that we are losing all those benefits. So we are not really, overall emissions are not increasing and the pollution is not increasing. This is the pet coke. There was a case against pet coke in the middle, so there was a little ban, but then those numbers are also increasing. The pet coke is really important because it is the highest amount of sulfur content in it. Biggest users of pet coke are basically cement industry and fertilizers. And we do produce a lot of cement and fertilizers in the country, and the emissions from that are significant. And overall, the electricity consumption in the sector is also quite high in all the sectors. The reason I'm putting this up is because the electricity is coming from the power plants, and majority of our power plant, 55 to 60% of the power generation is still from coal-based resources. In fact, in the last quarter, we had a biggest jump in the coal installation that happened in the country in almost like 5 years. So when the new power plants have come into play, and that is when the demand is there in all the sectors. So obviously, the expansion is still continuing to grow, even though we are expanding the renewable energy side of the story as well. So all these things are basically showing us that that even though we are improving on the technology, we're improving on understanding what's good for us. The overall emissions are continuing to increase. They're already increasing all the time. This is the latest paper from Chandra Venkatrama's group at IIT Bombay, looking at the emissions side and also at the PM 2.5 side. So what are the contributions coming from various sectors in the areas where the pollution is high and low? No, it's a great picture, and basically looking at this is where the core science actually comes into play. If you look at the areas with the highest pollution, is 110 to 140 micrograms per meter cube, your biggest contributions are coming from the organic and inorganic species. Okay, so which means that no, this is not just pure emissions coming from the source like BCOC formation, but it's actually because of all the chemical reactions that are happening in the atmosphere, because of the amount of the load of emissions is so high from those species. So this organic aerosols, obviously, it's a combination of or direct organic carbon and a combination of secondary organic aerosols. So if the emission loads are so high, so obviously these are contributing a lot more in the region to these sectors, and these are primarily coming from if you try to correlate between these two, cooking and heating sectors are contributing a lot, and this portion 110 to 140, this is pretty much in the Indo-Gangetic Plain area, and the other regions are basically Central India area, and then you have a lot of South and Northeast regions that are at the bottom, where we have a lot more direct emissions impact on the air quality. So this is where I think a lot of direct science of aerosol science comes into play. If we want to create a holistic policy to control PM 2.5 as a whole, where do we focus our efforts, and then what is science telling us in each of these? And I want to shift gears a little bit on the air quality data stories, because I mean, at the end of the day, it's not about just the science part. Maybe also are trying to focus on and trying to help the public bodies as well. So what do they see in aerosol science? We do have air quality index that was issued in 2014, and we have 6 different categories, and then we have defined these numbers for all the criteria pollutants. So this is where some of the research opportunities exist, where we really need to expand a lot more. As you can see, the monitoring capacity has increased over the years, but when we are still focusing on the first column, most of the cities are still with only with one station only. Mathematically speaking, it's not a good number. Okay, we can use this saying of beggars can't be choosers and start using this information, but it's not really giving us a true ground reality of air pollution in the cities. This is a summary of all the air quality index bulletins over the years. One could interpret this as saying that, okay, our winter time numbers are increasing, but then the mathematical side of the story will tell you that if we are increasing the overall representation by increasing the number of stations, the numbers will start getting average out, and then you will start seeing a little lower number. That could be a possibility as well. But now, is it truly improving or not? No, that's a toss up. If we start looking at the satellite imagery, when we see that things are not improving so dramatically. Delhi is the most represented area with more than 40 monitoring stations. And as you can see, things are changing, but I won't dramatically, I won't put a finger on it and say that, okay, it's dramatically improving to be good. And the winter time continues to be worse. Something similar for Mumbai. I put this up because Mumbai has been in the news a lot more recently. As much as it has been for Delhi. And we can see that the air quality index is slowly creeping up. Now those orange numbers have showed up suddenly, which were not there before. Now it could be a combination of everything. The transportation has increased, industrial loading has increased in that area, brick kiln capacities have increased in that area, especially in the Thane region. So all of them are contributing to the air quality problems. So this is a very interesting slide, especially from air quality perspective. In the air quality bulletins, all the bulletins are required to also show, okay, why is that air quality index high? Is it because of PM 2.5, PM10, SO2, NO2? Which pollutant is the conditional pollutant that is putting that number up? If you see over the year, the share of PM 2.5 has reduced. It's going down and down, especially from 2019 or so. It's dramatically actually like going down more and more. And correspondingly, PM10 has increased. Okay. The theory behind this is basically the NCAP program. In the NCAP program now very specifically says that, okay, cities have to improve PM10 pollution by 40% by 2026. So what happened because of that is like more cities are actually reporting PM10 than PM 2.5, even though they're measuring all the other pollutants as well. And that is being used for air quality index in the pollutants a lot more than the other pollutants. So this is something that we should definitely, from a science perspective, we should definitely keep this in mind, that for us from health perspective and science perspective, PM 2.5 remains a critical pollutant, a lot more than PM10. But now from a regulatory perspective, things are actually shifting to the other way. Coming back to the same thing, this column, number one, number of cities with one station, it's a sad thing. This is something that we really have to shift more towards the right. I think this is where we have a lot of opportunity to expand. A city with only one monitoring station, it's not mathematically a good sample. Any given day, any city, we should have at least 20, 30, or 40 monitoring stations where you can have a good spatial and temporal representation, and something that we can use for both science and for regulatory discussions. We can expand this by using low-cost sensors, and that is changing. That picture is changing. A lot of groups are working on this, but the challenge has always been in calibration of this data, and then moving to a better framework where we can integrate all this, that entire system into the works. I'll shift a little bit more towards the modeling side. I think this is where things get a lot more interesting, especially for me, because we do a lot of the modeling work. The monitoring work is something that we only borrow information from different groups, but modeling work is something that we do to the core. It's an exercise which is a very involved exercise. It requires a lot of information at a lot of different stages, right from building an emissions inventory to doing a full-scale meteorological modeling that can be a direct input to the chemical transport models. And that is something that we can then start using for a lot of discussions, for spatial temporal analysis, for source apportionment, or for building a action plan that can be used for both regulatory and science discussions. So this is the last loop that will continue forever. But a lot of information has to go in. I mean, it's not something that we can click a button and start doing all these things. And this modeling part is something which has been a weak section in India in general. I'll quickly go over why I'm calling it a weak word in general. In the textbooks, we always read there are three types of models. We have box models, plume models, and Eulerian models. And there is a lot of complexity in each of these. Even though I say the complexity in the box models is very low, but I love the box models because it actually helps you understand the chemistry part, the science part a lot more faster and easier than the other models. So don't underestimate the box models. So please do use them as much as you can. A quick example of some of these models. I won't go into all of these. When you will have access to these presentations afterwards. Generally speaking, Eulerian models, those are the best models that we have access to, and we should definitely focus more on using those models much more. What used to be a sore point in using these any of the models are now defaults, and that happens in the Eulerian models. So, for example, boundary conditions. Now, the big question that comes when we start talking to the cities is, okay, how much of the pollution that I'm seeing is from the local sources, and how much of the pollution is coming from outside the city's airshed? Can we define that? Can we put a number to that? That can easily be done using Eulerian. Easily is a relative word, so take it with a pinch of salt. Because we have to define proper boundary conditions to the airshed in an Eulerian model, it basically allows us to understand what's going in and out of the airshed. That gives us the number. Photolysis. Now, if you run the system with a full chemistry, full emissions inventory, with proper speciation to VOCs and everything else, you can do a lot of science work. And then we're expanding your work not only to just to PM 2.5, but to all other criteria pollutants as well. This has become a default setting in these models. And then the MET interface. So not only we're not focusing only on sources, inventory that is localized to your airshed only. We can combine that with MET, and we have a lot of pre-processes that are there easily available. Then that can include your dust emissions, lighting emissions, sea salt, open fire, biogenic emissions, because all of these play a critical role in understanding what's happening to PM 2.5. And that's whether it's coming from secondary organic aerosol science or from the inorganic aerosol science from sulfates and nitrates. All of these are really, really important factors. And all of them are critical in the Indian subcontinent. They're not small numbers. I mean, we can't ignore them. Okay. The reason why I say that, for example, dust. I mean, the reason why our air quality standard for PM 2.5 is 40 micrograms per meter cube is because we are a dusty region. Okay, so we can't ignore that. And that dust is not coming only from local sources; it's also coming from natural sources. So we really have to take that into account. And now the new state-of-the-art Eulerian models are accounting for that. So the data and computational costs are high. We understand that, and the experience needed in running these models is also very high. So this has been the biggest bottleneck in expanding a lot of the modeling work that needs to happen in India. There are new reduced chemistry models where you can get 90% of the results using like 3 to 4% of the effort. But to get to this stage, you still need to run a good full-scale chemical transport model, a Eulerian chemical transport model to be able to take that next stage. So what we did is we did a quick landscape analysis of what kind of articles that have been produced in India. This is again to make a case where that we are not doing enough on the modeling side. There are only a handful of groups who are running these models, and that has to change. Very unique papers that we saw are about 220 unique hits. And that's expanding the number of articles on air quality in India, but not as much as it should. And very strict cuts on different topics, both for India and China. You can see that no, we are at least 4 times less in terms of producing these articles than in the other fields. Then we also did a very specific cuts on the monitoring side, emissions inventory side models, and pollution modeling papers. A lot of work, as you can see, about 60 to 70% of the papers that we see coming out of India are based on monitoring data. No, and I call them put, get, plot, present papers. When you basically have a monitoring station equipment, you put it somewhere, you got some data, you plotted it, and then you're presenting it as a paper. A lot of these papers are around exactly, they follow that pattern. um, and um, and then again, it's all the source of person papers are also exactly the same. You put a equipment, you do the chemical analysis, and you present that information, and you have a paper. I'm not saying that's the wrong thing to do. I mean, that's also very much required. But what we feel is a lot of work, a lot of focus is still on the monitoring side, and we need to make that jump into bringing that into the models and start doing a lot of modeling work. The inventories work. Majority of the papers are focusing on CO2, not so much on the air emissions side. Again, very few inventories that are coming out for different cities and for all of India, which are in use. A lot of papers that we see focusing on equality in India, they are using global inventories and not localized inventories. And on the pollution modeling side, majority of the papers are on meteorological modeling, because when we have the WARF, which is state of the art, a lot of the WARF community is very strong, and they provide you with a lot of information. And a lot of more papers, majority of the papers on modeling are meteorologically driven papers. On if we go back very, very, very specific on air quality modeling only, I mean, that's only like 6% of these papers that we found were easily used. And I mean, this is something that we also noticed, that when the monitoring papers are easy to publish, again, the reviewers come back with lesser comments. And on the modeling papers, the reviewers come back with some really, really harsh comments. I mean, it's basically we have a lot of gaps in the data in the inventory, and also on the modeling side, we're struggling that part. We're struggling with it, and then trying to improve those gaps quite a bit. But the comments don't help. So what happens is a lot of papers focus on monitoring rather than modeling. And the models themselves, the WARF papers are a lot more higher, WARF and WARF Chem, because the community is so much stronger in supporting installation of that now in trying to go through the any problems that we have on compilation or running. It's much more stronger. So obviously, a lot of papers that we're seeing focus on WARF. The models that we really need to run in the country to study PM 2.5 or aerosol science, that is CMAC and CAMX, the number of applications are really low. Yeah, I mean, this is something I take it very seriously, and this is where I think the even the Aerosol Science Association here, they really have to take a very serious note of this. Now, why are we not having some serious aerosol science modeling papers that are there in the journals? A lot of these global models at the bottom, Shimmer, Mozart, Xylem, Geoschem, they're all running outside India. I mean, they're not running here. And there are some Indian authors on these, but primarily driven by groups outside of India. So within India, when we have a very few of those running as well. So we do have a lot of gap. So as I said, computationally, things are very difficult. So there's a lot of barriers there, and then also the personnel needed are also missing. So this is where the point that I made earlier in the very second slide on the feeders, the capacity to interpret. I call this not just getting a model, install it, and run it, and get some results, but we also need the capacity to interpret. So this is something we really need to start improving both at the institutional level and also at pretty much all the levels actually. So we have a large potential to go after the traditional chemical transport modeling. Okay, and my personal choice are obviously the CMAC and CAMEX models, where you have a lot of flexibility in studying aerosol science to a lot more depth. And this is, I think, something that we should take definitely more seriously. So I have three more slides on general research opportunities. Like, where do we go from this? Now, we have a good understanding of what our pollution levels are, a general understanding of what are the sectors that are contributing to our problem. We have a general understanding of the breakup of aerosols that we are measuring, because we have a lot of source apportionment work that happens across the country. We do a lot of monitoring from a research perspective. We so what can we do little extra from at this point? So we, on the monitoring side, we need to step up a little bit. We need to go beyond that put get plot present mode. Now we have to combine some of the results that we're getting from the monitoring work of the story to the modeling side. So I'm not talking about just the receptor models where PMF and CMB work that happens, but we have to start connecting it to the source based, emission based models as well. So that part of the connection where both sides of the story have to talk to each other, that is definitely is missing. Where you have very, very few papers that are there that do both your receptor modeling and source modeling at the same time. I think when we do that, we can then take a leap into supporting the regulatory part of the work with direct science. I think that is definitely is missing. When in NCAP they talk about it, but cities definitely are not doing it. I think this is where I think the aerosol science community definitely can step in and do a lot more. Again, quick questions. These are something, if you do a search on these core topics in the literature, focus on India, you will find literally papers that you can count on your fingers. It's like, why is that? Now, if you do the same thing for US or Europe, you will find like hundreds of them. Okay, so this is where I think when we are doing a lot of the monitoring work, we're like focusing only on the top side of it. We have to dig deep. Okay, now what is the role of inorganic secondary pollutants? Now the Chandra Venkatraman's paper that we saw, when we see a lot of sulfate contributions, nitrate contributions coming into PM 2.5. So if we want to drive policy discussions, now can we drive the policy discussions from the inorganic part of the aerosols? Now, what needs to be done? Now, what can we model within any of these models to understand that story? Same thing with the organic secondary air pollutants. When it comes to October, November, December on the Indo-Gangetic plain, when the fires start, we have so much contribution coming from secondary organic aerosols. Okay, when we talk about overall PM 2.5 pollution and haze, and the winters are bad, but we don't dig into the fractions. Okay, so why is that haze high? So how much of that is driven by the organic aerosols? How much of that is driven by the photochemistry that's happening between ozone, NOx, and VOC? I mean, you look at the papers, very handful of papers that are there in the system. Now, role of dust on secondary chemistry and ozone. When we know that the dust provides residence time to reactions to take place. Okay, and we have a lot of dust in the atmosphere, especially when we talk about dust storms that happen or road dust that gets resuspended. I mean, this dust provides a lot of retention time for chemistry to take place, and that chemistry drives the secondary organic aerosols formation and also the inorganic aerosols as well. So what is that role? We've not studied enough of that either. The photochemical regimes that I just mentioned, when we are changing our fuel mix, I mean, if you take the transport sector, we are pushing away slowly from petrol and diesel to EVs. So if we are going to do that, if the shift is going to happen, what will it have? What kind of effect will it have on the photochemical regimes? Okay, on the both on PM 2.5, obviously we'll see a reduction in that, but the ozone side of the story, we are completely losing that. Impact of land use changes. Now, biogenics are a really important element in our atmosphere, and if cities are moving away from green land use, if they are going becoming more and more urban, more and more built up areas are coming up. If you look at any city, you did a quick analysis of that. Now, most of the big cities, tier 1, tier 2 cities, they have increased the urban built up area at least 4 to 10 times. Okay. So what kind of effect does it have on biogenics? Because biogenics are really important. Biogenics help reduce the ozone pollution in the cities. Okay. If we are taking that out of the system and that's only been confined to the rural areas or forest areas, now what kind of impact does it have on both on aerosol science and ozone science? So these are the kind of questions I think there's a lot of opportunities that are there that we still haven't explored enough. There are bits and pieces happening here and there. Different groups are working on small things, but this can definitely be expanded to a lot more than available. Last slide. There are a lot of papers that are coming out on machine learning and artificial intelligence. Now, I really don't agree with any of them because this is not the answer for us. I mean, we are still, a lot of core work needs to happen still. Okay, only then we can take the sleep. Till then, please try to restrain yourself from using this MI AI kind of work. It is not a solution for us yet. Okay, we still have a lot to learn. We still have a lot to a lot of data to collect and a lot of data to to analyze. So let's build that capacity to interpret. Okay, so I'll stop there. Thank you.
Okay, thank you. Thank you so much, sir, for such an interesting and informative talk. And it covered a very broad range from measurement to modeling. So, and one more thing I would like to tell before I ask my other friend for further proceedings. You kept our show houseful. Means we have a capacity of 100 people and they were overflowing. So I'm sure there are many questions, and I would request Dr. Abhijit Chatterjee to take care of question answer session. Abhijit, can you please take over?
Yeah. So thank you, Sarath. It was indeed a very insightful and engaging talk.
Thank you.
At least you are the first person that I have heard that the way our Indian scenario on the aerosol research or air pollution research is working on, the way that you have shown, it was really nice. So thank you, Sarath, once again. So we have some questions that was put in the chat box. So I can read those. Okay, so hope Sarath, you can address all of them. Some questions were there that what is the reliability of the data reported by the University of Chicago? Probably he or she is referring to the AQLI, maybe air quality.
AQLI,
So your response, please. What is the reliability of this data?
Reliability is a toss-up. When all of them are models, and they're basically using whatever best they found useful, and they ran the global models and came up with that information. So the reason why I put that up is because that's a metric. I mean, that's the only metric. If we had the same metric coming from the Indian organizations, then we'll definitely use that as well. Because I mean, even from the health impacts perspective as well, we continue to go to the global burden of disease GBD results because they are the only ones putting those numbers out on a regular basis. If we have a similar system in place, I mean, we'll definitely use that. So I mean, reliability is something, it's a very shaky ground. It's just a metric to get the conversation started. But we know that health impacts are important, and here's a metric, and here's a method that's there that can be used to to tell a story. Yeah.
Okay, and thank you. And many want to learn that I mean, probably they are the new research scholars, they are new in this field. So they just want to know how to start learning about the modeling, air quality modeling, if they do not have any idea. What is the right thing to start with to begin with? So if you can respond.
Excellent question. I mean, this is something that I personally have been struggling as well. Like, how do we teach modeling? On our website, we have under research, there are tools to jumpstart how to run models. So, I mean, we created a set of tools there for emissions inventories, for scenario analysis, and also for benchmarking these meteorological models and other models as well. So that's a start. But you really have to uh, to basically download the model, run the test cases, crash the model a few times, see what kind of errors do you get. That's the only way. I mean, it's not something that you download and then everything will be running in a week, and that's not going to happen. There's always a learning process. So best is you have to start that I want to run the models, to use the forums. All the models have forums, like WARF has a forum, CMAC has a forum, CAMEX has a good forum, all the forum of community users. And if you have a problem, post it. Then somebody will answer. Or the forum itself. I mean, these forums have been around for more than like 10, 20 years. So there are a lot of questions. If you are experiencing a problem, somebody had that problem before. No, there will be an answer somewhere. So go through that. Then come to us now, even on urban emissions or any other a couple of other groups. Come to us, send us an email. If we can help you, we'll help you.
Thank you. And another question was, right, what would be the base model for atmospheric chemistry? I think, sir, it would be the WRF chem, right? It would be the best option for atmospheric chemistry.
That's an integrated model with metrology and chemical transport modeling together. So you can go with the WRF-Chem. The reason why I don't use WRF-Chem is because of the computational capacity needed to run WRF-Chem. It's a lot more higher. So the next step will be using the CMAC and CAMEX, where things are broken down. So you're not so much attached to just one system and you have to wait for the whole system to run. So you can run WRF separately, and you get all your meteorological parameters and all the pre-processes for run through WRF. That will be done. Then you pick. So if your focus is only on air quality, for PM 2.5, ozone, CO, VOC, secondary organic aerosols, CAMEX is an excellent model. Yeah, it does most of the air quality analysis for you. It does. It has integrated ozone source apportionment, particulate source apportionment. You can do a lot of things in it. And on top of that, okay, I'm not only interested in PM 2.5 or like aerosol science, but I'm also interested in coupling climate change. Now I want to study radiative impacts of aerosols. If the scenarios are there, how is that changing the radiative forcing in a city or in a region? Then you will have to go to CMAC, where you have the option of doing that coupling modeling. So anything you keep adding to your agenda, the models are there, your complexity also increases, your data needs also kind of go up, your computational needs also go up. So if like pick a portfolio first. So if you're talking about air quality only, like pick a model where you don't have to do things more than what you need. Okay.
Yeah, along with the air quality, we should also have the climate co-benefits. So some models could also work. So another question is a very interesting question, that what would be the optimal solution to get rid of the Delhi's air pollution? Just switching off the vehicles. So yeah, Sarath. Yeah.
I mean, there's no optimal solution. As I said, pollution comes from all the sources, and then Delhi is in the middle of um, it's a tight knit place. I mean, it's not just emission control that happen only in Delhi. I mean, if that's the case, then things have improved a long time ago. So it's also about the region. So the entire Indo-Gangetic plain has to basically clean up at a significant level to reduce the overall pollution in Delhi cases. Because in Delhi, the outside contribution from the Delhi administrative boundary is close to like 50%. So, which means that not only controlling emissions in the city, which is primarily transport sector, a lot of things has to happen on the brick kilns which are outside, all the power plants in the region where the power comes from for Delhi, because Delhi stopped producing their own power. All the power plants are shut, and then only the Jhajra, Jhajjar and Dadri, they are the only ones producing, and very little. But demand is much higher than that. Your cooking and heating still is a huge demand, and not only in the city but also across the region. So a lot of things have to happen in everything. Now, waste management has to clean up quite a bit. The transport sector, especially on the road, on the dust side, has to improve quite a bit. The cooking and heating. Cooking is fairly good because now a lot of communities have piped gas line for LPG, but the heating side of the story is still very meek. Now, if you go to any of the regions, especially in the November, December, January area, a lot of groups are still using wood and waste for heating purposes. That really has to change. So solutions are there now, but I think it's still going to take some more time.
And we should also stop spending money towards fighting this false solution like smoke tower. Like
absolutely.
So another interesting question was, as the dust is an important constituent of aerosols in the Indian scenario, but there is hardly any model which exclusively address these dust emissions and transport or evolutions. So in other words, the parameterizations of dust properties in modeling in Indian dust. So can you?
So no, the parameterization exists, whether you take WRF-Chem or CAMEX or CMAC, any of these models, parameterization exists, and a lot of understanding is there on how much emissions are coming from the natural dust, like natural dust, especially dust storms and all. That is there, but like I said, the focus on how dust is contributing to the secondary organic aerosol chemistry or inorganic chemistry, that part is still studied limited. Those studies are very limited in India. I mean, that really has to change. Models are there. We are not using those models in this direction because probably inputs are not clean, especially on the emissions inventory side, probably. So if we can improve that, and we can have some dedicated groups working on that, and that definitely will change. Now, I know that IIT Kanpur, both Mukesh Sharma and SNT's groups, they do a lot of those secondary organic aerosols work, and even like Vinayak Sinha at ISRO Mohali, they've been doing a lot of that work in that area. But again, a lot of that work is still happening only on the monitoring side. I think that really have to take a leapfrog into the models and then start applying those.
Thank you. So Neeraj, can we take one or two quick questions, maybe? Or
I think that should be answered by Sarath. Sarath, is it okay to
Sarath, is it
discuss?
okay?
Yeah.
Okay. So I would like to read another interesting questions like someone has posted Sahu that I think the AQI has to be looked very differently than what is followed now. The health impact will be much more when the interaction of the pollutants happens. Presenting separately to AQI should be revisited. What's your opinion on? Yeah, it's
no, I absolutely agree, and even the new change that happened in NCAP to focus only on PM10 actually derailed this discussion. Because what happened is, if you're only focusing on PM10 because that's been asked to control, then that interaction question, like the focus on the other pollutants, has completely gone out of the picture. So I think we need a change. If there is an NCAP 2.0, we need that change. We don't want to focus only on PM10. That line has to change. It's not about 40% reduction in PM10. It should be 40% reduction in air pollution. So then what happens is, then we get all these interactions into play. No? So it's not about just, no, if I reduce SO2, so automatically the sulfates will go away and my PM 2.5 will drop. No? If I'm controlling systematically both NOx and VOCs, I will have a good drop in both nitrates and secondary organic aerosols in the region. Okay, that is a benefit directly to PM 2.5 and PM 10. So I think that change at the top level, these wordings have to change so that we can get this interaction of gases and aerosols into play.
And another one was, what's the scope of the application for artificial intelligence and machine learning models like Aurora from Microsoft in the Indian context, in the research of air pollution in India? Right.
Yeah, and the scope of this, scope of this AI ML is very high. I'm not denying that, but conceptually speaking, how does this AI and ML model work? So it needs a lot of data. No, so for example, I'm sure everybody uses here Amazon to order things. You've ordered surf or something or toothpaste or something, 2-3 months ago. So what happens? That model basically says, okay, this person has ordered a surf 2 months ago, so he or she must be needing surf again now. So the model tells you that. So that because that model has a data point to rely on. So the same thing. We need the data. We need lots of data to make that call, saying intelligent call. I think we need to build that data. We need to build that science. We need to build those interactions between monitoring data and modeling data on those predictions. No, if I'm going to control SO2, how much am I going to control sulfates? If I'm going to control NOx, how much am I going to control NO3? So that part of regression, that part of the science work is still pending. If we can build that data a lot, we can then start using all of these new tools. But we can't build a tool based on one monitoring data. Now you go to I don't know that Birinath in Meghalaya, so it's always on the top, but it has only one station. I mean, you can't build a intelligent system using one station data. And most often, the data station is also at the pollution control board. I mean, is it really a representative station? No, we can't build an AI model on top of that. We have to build the database. Then potentially it's immense. Yeah.
And the last one, somebody has asked that, can you suggest some simple models which can be used for experimental researchers to predict their experiments? For example, SOA formation from a particular VOC at different temperature. Before Sarath can respond, I will say it is hardly possible. I think the chamber studies would be the best option for such kind of thing. Yeah.
Yeah. So basically, you have to have probably when the person asks Deva Prasad, you're probably doing some chamber experiments already, so you have some equation on SIA formation and stuff. So if you want to run that in a model, like best is a box model. No, that's a simple model. So you basically take boundary conditions from any of the regional models, start with that, and feed your input into that, and see how the chemistry changes over 1 day, 2 day. So box models are really, really useful in trying to understand the chemistry. If they provide you with results that are useful, then you can incorporate that into bigger models like CMAC and CAMX and see what happens.
Okay, Sarath, thank you very much.
Okay,
it was quite overloaded.
Abhijit, if you allow, can I also ask something?
Yeah, please, please.
Sure.
Okay, so just one thing. One thing you mentioned about people who are doing measurement versus modeling over India and number of papers you were talking about. So means I come from one type of group. So just one thing about that. So is it not expected? Means when we are doing measurement, so that means if we are going at different places, different season, means things will be different. But when you are doing modeling, say once you have put some concept, and since model can be applied to a bigger region. So once you have put something, then it was, unless you are changing, okay, now scenario was earlier like this, now scenario is changing, or meteorology is changing, or emissions are changing, then how things will be. But and then also measurement means are needed to validate whatever you are predicting, means in a long term, whether means they have to be there.
Yeah.
So
No, I completely agree. I mean, I didn't mean to say that, oh, I mean, we are putting too much, we're doing monitoring and not modeling. I think we need to make that jump. Now, like you said, we need a lot of monitoring data to validate the models so that models are actually uh, uh, representing the reality of what's happening on the ground. That needs to happen. That definitely needs to happen. But what I'm saying is that if we can couple the monitoring work more with the modeling work and not just stop at saying that, okay, I put this monitor, I got this data, and here's my plot. Now, let's not stop there.
yeah.
I think let's combine that with the modeling work.
Right.
Then we have, I think, a lot of power.
Correct. So my next question was that only. So means how we can shake hand. We can means measurement people versus modeler. Means how can they shake hand so that both are getting benefited and ultimately science is getting more benefit. That means measurement also, that data is applied for a bigger thing, and modeling also they are getting the real data to means proceed with. So means
I think that's where the association comes into picture, right? And when you have the perfect platform to make those handshakes happen. So, I mean, people who are working in the monitoring
we are
field,
providing platform,
people,
but people have to come and
And Neeraj, with the measurement, people also receive harsh comments from the reviewers, not only the modelers. And Sarath, Dr. Ashutosh repeatedly making a request to clarify one thing, just the last questions, that he wants to know that do you think including hyperlocal sensor-based air quality measurements would help the data gap and improve physics-based and machine learning models? Hyperlocal sensor-based air quality measurement,
I mean, when you say hyperlocal, I'm assuming that you're collecting a lot of data. And so obviously your data pool increases, so you can definitely have a much better fit and a much better regression models in those ML models. And but then it's a very localized interpretation. So if we want to make that into a interpreted model for a larger region or for larger policy discussion, then you need a lot more data. So for the hyperlocal experiment, excellent, it works.
Just for a quick response from you, maybe within a second or so, that as we know that NCAP is mainly focusing on the 131 cities in India. Okay, so but actually we are not addressing the rural atmosphere in India where the emissions are quite high. Okay, so do you think that we should immediately move to airshed approach rather than the city-based approach if we really want to make some holistic policies for the nation?
Thank you. I think you're basically allowing me to plug in my own latest paper. I mean, we try to define these regional airsheds to basically answer exactly that question. I mean, if we are focusing only on the cities, we are only addressing about 30% of our problem. And 70% of our problem is actually on the rural side, both in the population load, both in terms of pollution load. So if you want to address that, and also the question, the earlier question, we want to also understand how much of pollution is coming from outside. That Delhi question, for example, the Delhi can't answer that problem, their question with just focusing on their internal work. They really have to go outside as well. That can happen only in an airshed approach. So maybe in the NCAP 2, the next round of NCAP, instead of focusing on 131 cities, they should start focusing on airsheds. Right? If we define, when we put out an example of like 15 airsheds for India using agroclimatological data, and did some analysis on that part. But I mean, that's not just, I mean, that's just one idea, but it can be a lot more than that. But we have to definitely move away from the cities and talking about regions and do some holistic planning.
So thank you, Sarath, for such a wonderful and insightful, informative and innovative kind of approach of or the scenario of Indian air pollution research. It was really wonderful, and you made our show houseful. So thank you very much. And I also like to thank the audience for their for making it a big success and putting all the relevant questions. And I'm sorry that I probably might have missed one or two questions from your thing. So I just read only the relevant questions, and that would be the best answered by you. And I would also like to thank the Vice President of IASTA, Neeraj, Manish, the Secretary of IASTA, the entire IASTA team, and the EC members. And I would also like to thank the TestCon India for sponsoring these online IASTA lectures so far. So, Neeraj, thank you all. So, shall we end here? This 14th lecture series.
Yeah, just I will make one comment. Means not related to this talk. I have seen some of the questions, Manish. Some people have written about this. They have done this, this lifetime membership, but they are not getting the confirmation or something.
Yes, I replied.
Okay.
Correct.
Yeah. So
Yeah,
okay,
I
so
replied. So we'll
okay.
take care. So
Fine. Okay. Thank you, Sarath.
So, yeah,
Thank you.
Sarath.
Thank you.
Thank you, sir.
thank you, Sunita. Thank you, Sarath. Thank you, everyone.